You wire up 5 buttons in a loop. Button 0 should log 0, button 1 should log 1, and so on. You run it, click each one, and every single button logs the same number, 5. Not 0. Not 4. 5, 5, 5, 5, 5. You didn't misspell anything. The loop ran exactly 5 times, exactly like it should have. So why does every one of those functions remember the same final value instead of the value it was created with? That bug isn't random, and it isn't a JavaScript bug. It's JavaScript working exactly as designed, and once you see the mechanism behind it, you'll never guess and check your way through a bug like this again. In the next few minutes you're getting 5 real engines running under every line of JavaScript you write, how variables actually get found, why some errors happen before your code even runs, how this quietly changes meaning depending on how a function gets called, why class in JavaScript is a costume over something much older, and the real order your asynchronous code executes in, not the order it's written in. This is the stuff senior developers know cold, and nobody sat you down to actually teach it. Think of every function call as its own room. When a function runs, the engine builds a new room with its own variables inside it. If a variable isn't in that room, the engine walks out into the hallway and checks the room outside it, then the room outside that, all the way back, never sideways into a neighboring room, never guessing at runtime. That's the scope chain, and it's fixed the moment your code is written, not while it's running. A closure is just a function that keeps its hallway door propped open. It remembers the path back to its outer room even after that outer room is technically done running. In your 5-button loop, var puts all 5 listener functions in the exact same outer room. By the time any one of them actually fires, that shared rooms counter has already finished counting all the way up to 5. They're not 5 separate memories, they're 5 different doors into the exact same room. Swap var for let, and JavaScript builds a brand new room for every single loop iteration, so each closure locks its own door with its own number sealed inside. Before your engine runs a single line, it does a fast pass over the whole scope to figure out what names exist. Like a stage manager reading the entire script before opening night, so every prop is already in position before the first line is spoken. Function declarations get placed fully on stage, ready to use. Variables declared with var get a name tag reserved in advance, but nothing written on it yet. Reach for it early and you get undefined, not a crash. Variables declared with let or const get a name tag reserved too, but the engine deliberately fences that name off until its real declaration line. That fenced off stretch is called the Temporal Dead Zone, and touching the name inside it throws a reference error on purpose. Same reservation mechanism under the hood, completely different rule about how early you're allowed to touch it. Modern JavaScript intentionally traded the silent undefined footgun for a loud crash, so the bug surfaces right where it happened instead of 3 functions downstream. This isn't glued to a function the way you'd expect a name tag to be. Think of it less like a name tag and more like a walkie-talkie that only knows whoever's currently holding it. Call a function as object.method, and this is whoever's standing to the left of that, the object holding the walkie-talkie in that exact instant. Detach that same function and hand it off as a callback, and the walkie-talkie gets passed to someone else entirely, usually the button that fired the event, or nothing at all in strict mode, because what decides this isn't where the function was written, it's how it got called this specific time. Arrow functions break that rule on purpose. They never pick up a walkie-talkie of their own. They just borrow whoever's holding it in the room they were written in. Lexical this, the exact same rule as the scope chain from chapter 1. That's the real reason just use an arrow function fixes so many this is undefined bugs inside event handlers and callbacks. JavaScript objects don't inherit from a blueprint the way a class does in a language like Java. They inherit through a chain of actual, living objects, each one pointing at the next. Ask an object for a property it doesn't have, and instead of failing immediately, the engine walks up that chain, the object, then its prototype, then the prototype's own prototype, until it either finds the property or hits the very end of the chain, which is null. The class keyword, added in ES6, isn't a new inheritance system underneath. It's a friendlier layer of syntax sitting directly on top of the same prototype chain the engine has used since 1995. When you write extends, under the hood you're just wiring one object's prototype to point at another. You can watch this chain directly. Object get prototype of on any instance hands you back the exact object it's climbing toward next, and instanceif is really just asking does this specific object show up anywhere on that chain. It's the same walk up until you find it idea as the scope chain from chapter 1, just climbing between objects instead of climbing between rooms. Here's the part that reframes everything you just learned. None of those 4 mechanisms, scope, hoisting, this prototypes, decide what order your code actually executes in. JavaScript runs on a single thread, one line at a time, no exceptions, but it fakes doing several things at once with a very specific queuing system, and getting that order wrong is where some of the ugliest async bugs come from. Picture a single cashier, that's your call stack, and two lines behind the counter. One line is the microtask line, promise callbacks, then, queue microtask. It has priority. The cashier drains that entire line, everyone in it, before looking anywhere else, even if new people join partway through. The other line is the macrotask line, set timeout, click events, network callbacks. The cashier serves exactly one person from that line, then immediately checks the microtask line again before ever serving a second macrotask. That's why logging A, scheduling a set timeout that logs B, scheduling a resolved promise that logs C, then logging D prints A, D, C, B, not A, B, C, D. The synchronous code finishes first, then the entire microtask line drains completely, and only after that does the cashier even glance at the timer line. The 0 inside set timeout with a 0 millisecond delay was never a promise about time, it's a promise about position in that second line. Here's the part that stays genuinely confusing even once you know the mechanism. Async and await look like they pause your whole program the way a debugger would, but they only pause that one function's own execution. Everything else on the page keeps running underneath it. That's exactly why running for each with an async callback is a famous trap. For each has no idea its callback returned a promise, so it fires off every iteration immediately, back to back, and your sequential await never actually blocks the loop, a mistake senior developers still make when they're moving fast. And on the flip side, a chain of microtasks that keeps queuing more microtasks forever can starve the macrotask line completely, freezing clicks, freezing renders, freezing everything, without a single infinite while loop anywhere in your code. There's a smaller version of this same surprise hiding in the promise constructor itself. The function you pass into new promise doesn't wait for anything. It runs immediately, synchronously, the instant the promise gets created, before a single and callback is ever attached. Only that a then callback itself gets deferred onto the microtask line. Developers who assume the whole promise block is automatically async get bitten by this constantly. Understanding the mechanism doesn't make async code trivial. It just means when it breaks, you know exactly which line to interrogate first. So next time something in your JavaScript does the wrong thing, you don't have to guess. You ask 3 questions in order. 1. Is a variable remembering the wrong value? That's scope and closures, chapter 1. Check which room it's actually reading from. 2. Is a function acting like it doesn't know what object it belongs to? That's this problem. Check how it was called, not where it was written. 3. Is something running in the wrong order relative to something else? That's the event loop. Check whether you're looking at a microtask or a macrotask. Almost every JavaScript is broken bug report from a junior developer is actually one of these 3 mechanisms working exactly as designed, just somewhere the code didn't expect it. None of this got explained to you on day 1, because none of it shows up until your code is complex enough to actually need it, which is exactly why understanding it now puts you ahead of developers with twice your years of experience who never went back to check. Every single one of these 5 mechanisms was already running the very first time you ever opened a console and typed a line of JavaScript. You just didn't have a name for any of them yet, and now you do. That's the actual gap between someone who writes code that works and someone who can explain calmly exactly why it works, in an interview, in a code review, or at 2 in the morning when production is on fire. And if that stale counterbug from chapter 1 sounded familiar, it's the exact same mechanism behind the stale state bug we broke down completely in the use effect video on this channel. Go watch that one next.